So Gunther, you might want to try to share a screen, see whether it's working.
Yeah, sure. Hang on a second. Here we go.
Yes. Yes, I can see that.
Okay. Just a second. I need to get rid of some of the other windows, otherwise my slides won't advance. Okay.
Okay. Hello, everyone. We are very glad to have Professor Gunther Roland with us today. He doesn't need any introduction to any of us. He finished his PhD from Frankfurt in 1993, then was a postdoc at MIT and Frankfurt, and joined as an assistant professor at MIT in 2000, and now he's a full professor there. Today, he will tell us about the hot QCD with the sPHENIX program that will be starting this year. So once again, thank you, Professor Roland, to give the seminar today. And please go ahead, the room is yours.
Sure. Well, we're not going to start this year, but as I said, I will tell you all about that in a second. I just checked, as far as I can tell, the last time I talked about sPHENIX in Berkeley was 6 years ago, just after, shortly after we had formed a collaboration. And when we were trying to convince Berkeley to join us, I vaguely recall that that seminar lasted for about 2 days and 10 hours of me talking. So I don't think we'll have quite as much to talk about today, but let's see. So hot QCD with sPHENIX at RHIC, and I assume this is the picture that Xin-Yang was referring to. I'll come back to that later in the talk. Where do we start? We start with the big questions that we're trying to answer in heavy ion physics. Obviously, our goal is to understand the nature of matter, which inevitably will turn out to be strongly interacting matter at the highest temperatures and densities, similar to those in the universe about a few microseconds after the Big Bang. Okay, so that's, I think, the standard motivation for what we've been doing. And as some of you, not many of you, but some of you know, we've been doing that for a really long time, since the mid-1980s at AGS and SPS fixed target programs at collision energies that are 1 or 2 orders of magnitude smaller than most of what I will talk about today. I think, well, I wasn't there in the mid-80s, but not long thereafter, early enough to see the contraption in the north area at CERN that was taking these pictures of sulfur and gold collisions with a streamer chamber. It's not as big as the experiments that we're building today, not that much smaller, but it definitely made much more noise when the camera was actually taking the pictures. Okay, so today, of course, we are in the modern era, which I think by most people's reckoning started about 20 years ago, 2 decades ago at RHIC, with the first dedicated machine, a heavy ion collider, and the first set of really dedicated detectors developed to study heavy ion collisions at this collider at beam energies up to 200 GeV, so an order of magnitude higher than before. And then 10 years later, the Large Hadron Collider joined the fun with the top energy, another order of magnitude higher, and now a factor of 20 higher than at RHIC. And what I will try to motivate in the next few slides is why 20 years after RHIC started operations, we're now talking about installing a new detector at this collider sort of towards the end in the last few years of its lifetime. So that's the subject of today's talk. And well, to understand that, we can go back to the early 2000s, the first year of running at RHIC, where I think two early discoveries really set the course of the field over the next 2 decades and are still representing two of few main research directions in heavy ion collisions. I mean, you should be very familiar with that. I mean, one was the measurement of elliptic flow in gold-gold collisions by STAR, showing that at least for mid-central collisions, you started reaching values of the final state anisotropy that are in the ballpark of predictions from ideal hydrodynamics. And of course, that really set the stage for a large fraction of what we've been doing. And the other observation was that of a high PT, suppression of high PT yields of hadrons compared to an attempt to construct a proton-proton reference. And obviously that was the phenomena that we now know as jet quenching, related to parton energy loss in the Quark-Gluon Plasma. And again, that's one of the main directions that we are still pursuing. Since then, of course, we have learned from these measurements and many other measurements a lot about the properties of hot matter at the highest temperatures and densities. In particular, we have observed the near perfect fluidity and the extreme opacity for fast partons of that matter. And we have shown that the long wavelength properties of that observed new medium, the Quark-Gluon Plasma, can be understood in terms of relativistic viscous hydrodynamics, starting from a fluctuating initial collision state, where many of the properties, the structure and fine structure of the final state, directly arise from the hydrodynamic response to the initial state anisotropies. And then, of course, we have studied this in terms of transport coefficients, most famously in terms of the shear viscosity to entropy density ratio, eta over S, which is found to be close to a lower limit that can be shown or at least conjectured in certain conformal field theories, 1 over 4 pi in this dimensionless number. And we have determined with a similar precision the transport coefficient governing the propagation of fast partons through the plasma, Q hat, maybe E hat, relating to radiative and collisional energy loss. We have understood, maybe not quite as precisely, the diffusion coefficient in for governing coupling of heavy quarks or the motion of heavy quarks in the expanding medium, and a number of other properties of the Quark-Gluon Plasma. For most of these quantities, we have sort of, let's say, to within 20–30% determination of its average value. What has unsurprisingly proven much more difficult is to understand how these coefficients, the properties of the Quark-Gluon Plasma evolve as a function of temperature as you cross and then increase the temperature away from the phase transition or the crossover temperature between the hadronic and the Quark-Gluon world. So following from where we stand, a reformulated goal of the field is to use improved instrumentation at the facilities that we have to understand not just the QGP properties with higher precision, but to actually understand or see if we can understand how these properties arise from the underlying interactions described by quantum chromodynamics. Or in other words, we want to learn how does the QGP work? Okay. And this is sort of my go-to slide for that, with starting from these cartoons that Thomas Schäfer at some point 15 years or so produced. This, of course, is the goal that was described as one of the two goals for hot QCD physics in the 2015 long-range plan, which still is the governing document for our field in the US. I guess efforts to define the next long-range plan will start later this year. But for now, what we said we were going to do are two things. One is to map the phase diagram of QCD with experiments planned at RHIC, i.e. STAR, which had a very successful 5-year effort trying to execute these measurements. I will obviously not talk about that today, but I will talk about goal number 1, understanding how the QGP works through the complementary of two facilities, one being the LHC and the other being a new detector at RHIC called sPHENIX. Okay. The sort of importance of sPHENIX was, I think, very nicely highlighted in this document from the Brookhaven Nuclear and Particle Physics Advisory Committee, which, well, in hopeful terms says that in the next 3 years, we will see the culmination of the RHIC scientific program on hard probes, and that the PAC and many others look forward with great anticipation to the insights into the microscopic structure of the Quark-Gluon Plasma that the sPHENIX detector has been designed to deliver. So in the remaining, I don't know, 40 minutes or so, I will try to explain how sPHENIX is planning to deliver these insights, what are the design considerations that led to sPHENIX as we're constructing and installing it right now, and I'll show some of the measurements that we plan to do. Okay. As we said on the previous slide, the key goal here is to use hard probes to learn more about the microscopic structure of the Quark-Gluon Plasma. And if you map that onto the various observables that we have into the field, they fall broadly into 3 categories: jets, heavy flavor, and quarkonia. Of course, sPHENIX also has a very active cold QCD program, which, however, I will not talk about in detail. At LHC, in particular, the 3 categories of observables on the left are really studied by all the experiments, at least, but also in with great success by ATLAS, CMS, and LHCb. And I'm thinking back to the early 2000s and late 1990s I mentioned before. It's important to consider that the first generation RHIC detectors, Brahms and Phobos, which stopped data taking 15 years ago, and Phoenix and Star, where Phoenix stopped data taking about 5 years ago and Star is still going strong. They were designed with an emphasis on different observables, in particular bulk observables and rare electromagnetic probes. And to match the capabilities that we have at the LHC in the areas mentioned here, in particular with jets and heavy flavor, one really needs new instrumentation at RHIC, or it is possible to make with modest investments very great progress in the capabilities at RHIC. So with a new experiment called sPHENIX. The sPHENIX collaboration, I just want to say a few words. I mean, the collaboration was formed a little over 6 years ago. It has since grown to about 400 members from about 80 institutions in 14 countries. And well, these 400 people will be very busy over the next 11 months, as you will see in a moment. Let me just point out a little bit what the challenge was in designing sPHENIX. So the goal is to have complementary capabilities to that of those of the LHC. The challenge, of course, is that one part of that challenge, of course, is that the 4 experiments at the LHC in combination probably present a $3 billion investment. The compact muon solenoid shown here, CMS, in round numbers costs about $1 billion Swiss francs. Obviously, the DOE Office of Nuclear Science does not have $1 billion to spend on a new detector. So how do we make this an order of magnitude cheaper? Well, nature is kind to us. Okay, relativistic kinematics is kind to us by trying to implement this at an order of magnitude lower energy. You get much lower particle multiplicities. So you need spatial granularity that's some factor lower. The hard cross sections, if you scale them with XT, you find that where you might want to go to 1 TeV at the LHC, going to not quite 100 GeV at RHIC is going to be perfectly fine. And correspondingly, you don't need a 4 Tesla magnet, but 1.5 Tesla magnet that you find somewhere in the scrap heap at SLAC is going to do. And you can consequently also lower the granularity in your tracker, and your rapidity width shrinks. The one that you need to cover to capture most of the highest PG jets shrinks by about a factor of 2.5. So all of that combined allows you to save $1 billion and build a jet and heavy flavor detector that can do many of the same physics that the LHC detectors are doing at RHIC at an order of magnitude lower collision energy. And the scaling directly manifests in the size of the device, where CMS is 50 meters, Atlas is even bigger, sPHENIX is very compact, 5 meters in diameter. So these 5 meters are then filled with detectors with the usual shell-like structure with calorimetry on the outside, then a magnet, a superconducting solenoid, an electromagnetic, hadronic and electromagnetic calorimeter actually also on the inside, and then a tracking system consisting of a TPC and various silicon detectors that I will talk about a little bit later. The key here, and I'll stress that on various slides, is that there are some qualitative improvements compared to the capabilities at RHIC earlier. What we have here for the first time is a mid-rapidity hadronic calorimeter, complementing the electromagnetic calorimeter, allowing sort of the full calorimetric reconstruction of jets, as is used to be customary in high energy physics. And we have a new generation microvertex detector that really enables the heavy flavor program. And in terms of acceptance, this in round numbers combines the acceptance of the central part of star, about ±1 unit in rapidity, a little bit more, with the readout rate that Phoenix used to have of about 15 kilohertz for all the sub-detectors, and actually higher fraction of the collisions for the inner tracker. Okay, so that's what it looks like in a rendering based on the engineering drawings. And this is what the experiment looks like in real life. I will mention that later again, but the goal for sPHENIX is to start taking data in a little less than 10 months from now, in sort of mid-February 23. And well, if you want your detector to run in 10 months, you better have the pieces ready to go together. And here we see the outer H-cal that was fully assembled about 2 months ago around the 1.4 Tesla solenoid that we got from Baba. And this sits on a cradle where the whole experiment is going to be mounted. This is the outer H-cal. If you go inside, the next detector that we need is the inner H-cal, which by now also has been fully assembled and will be inserted into the outer hadronic calorimeter shortly. This work will proceed with great haste once the current RHIC run ends next week. Then on the inside of the inner H-cal, we'll have the electromagnetic calorimeter. It's a spaghetti design with scintillating fibers embedded in a tungsten epoxy matrix. And the last sector was just assembled last week. So these are now also waiting for installation. Let me just point out how this is going to help us. Here, I mean, you see the 3 elements of the calorimeter. I mean, one segment, one azimuthal segment of that outer H-cal, then the magnet, then inner H-cal, and the EM-cal. And if you have a jet, well, part of the jet part of the jet fragments will deposit the energy in all of these in this whole calorimeter stack with the highest granularity in the M-cal, then some in the inner H-cal and some of the energy in the outer H-cal. And then our task will be to properly calibrate the energies of the devices relative to each other, and then combine them into an event-by-event estimate of the energy deposition above an average background after subtracting the underlying event. And well, if we do that properly, then as in this fully simulated hijing event, we will end up with occasionally 2 jets clearly visible above the background. And I think the importance of having this calorimetric jets is really needs to be appreciated. We will use sort of relatively standard algorithms to, I mean, this is the Atlas algorithm documented in 10 years ago. This is one of the ones that we are using, which does an azimuthally modulated background estimate and subtraction to yield resolution of the jet energy that is at up to the highest energies that we are expecting to reconstruct, dominated or largely dominated by the underlying event fluctuations, which, well, depending on what your definition of a jet is, those can be considered irreducible. So the resolution of the device is as good as it needs to be to really be dominated by physics and not by detector effects. But the good resolution is only one thing. What, from my point of view, is at least as important is the fact that with this calorimetric jets, you can have an unbiased jet trigger, a fully efficient and unbiased jet trigger in PP collisions. And that will allow us to overcome a problem that I think the RHIC experiments and at least to some extent have faced, that while the enormous particle production in gold-gold or lead-lead collisions gives you, even with a moderate readout rate, gives you large statistics for many even rare probes. However, if you're not CMS or Atlas and can take PP collisions at a gigahertz collision rate, it becomes very difficult to get commensurate statistics for rare probes in PP collisions, and then in particular for PP jets. That's why occasionally we see things like RAA Pythia or RCP, which to me are always less than satisfying as measurements in heavy ion collisions. So with the hadronic calorimeters, we will be able to have an unbiased trigger on jets in PP, and therefore we'll be able to collect the maximum PP statistics that the accelerator delivers. Okay, so that's really one important aspect to keep in mind when you think about the sPHENIX capabilities. The other important part, except for the calorimetry, is of course the tracking system. As I said, TPC, a silicon strip tracker, the INTT, and then 3-layer MAPS-based detector as a microvertex detector. Here, I mean, again, these things have to be ready soon. The TPC will be installed in the fall of 21, according to our installation schedule. And one of the aspects that I would really like to impress the importance on you, although I think for the theorists, this business of TPC calibration, that's from your point of view, that's something that luckily happens to other people. But from the experimental point of view, this is really one of the keys to enabling almost all of the sPHENIX physics. In the TPC, where the charges produced in a large gas volume drift over distances of a meter or so to the readout chamber, you really have to control the distortions induced in this drift in the presence of a non-uniform magnetic field and in the presence of space charge generated in the collisions themselves and in the readout amplification. You have to control the drift of the charges over distances of meters with a precision of 100 micron in the transverse plane to preserve the momentum resolution. And this, I would say, is the apart from the detector building effort, putting the pieces of metal together, building the TPC calibration system is really the biggest effort in sPHENIX at the moment. I have 4 slides on that just to impress on you how important that is. I will not go through them. This calibration procedure has many pieces, including 2 different laser systems, a diffuse laser and a direct laser. The direct laser determines static distortions due to the presence of a non-uniform magnetic field. And the diffuse laser measures fluctuations around these static distortions. Then we monitor them with a new detector that we added to sPHENIX late, a couple of years ago. The TPC outer tracker that gives us a space point that is independent of the drift for a limited part of the phi acceptance. And then we monitor everything that is going on with the digital currents. And when we combine all of that, we believe that we will be able to reliably get a momentum resolution that is sort of in the percent range for most of the particles, and then at high PT increases to about 10% at 40 GeV, which is pretty good. It's not CMS good, but for RHIC, this is actually really quite good. And what does that buy us? It directly translates into the mass resolution for the upsilons. And of course, it's also extremely important if you want to resolve high Z charged fragments, hadrons, inside of the core of jets. And we believe that we can do all of that with fairly high tracking efficiency. So really the whole distortion correction procedure enables much of the sPHENIX physics program. Okay, and then there's the inner part of the detector, the INTT strip tracker and the MVTX pixel detector, 3 layers. Essentially a copy of the ALICE inner barrel detector. And I mean, everybody in Berkeley, I hope, is very familiar with that, because that's where a lot of the work for the NVTX was done. And that then allows us to open heavy flavor measurements in sPHENIX that go beyond what was possible at RHIC so far. I mean, compared to the HFT, I mean, this is maybe 2 generations. The star heavy flavor tracker, this is about 2 generations newer. It has a somewhat larger acceptance. It has a higher readout rate, less pileup. It is 3 layers instead of 2 layers, and consequently, I think we should be able to really make a big step forward in the heavy flavor capabilities. We have, of course, had this device in a test beam and verified the expected excellent spatial resolution, a few micron. And that translates in the ability to do a really very precise secondary vertexing. I will show some of the heavy flavor studies that we have been doing later. And they do not assume that we will do any particle identification with DDX in the TPC to further suppress the backgrounds. We will, of course, try to do that, but at the moment, our baseline for heavy flavor studies is just based on vertexing and the kinematic fits to suppress the background, as has been demonstrated successfully by CMS. Here is another technical detail for those of you who are maybe not so detector inclined, but for us, really a very clever way to go far beyond what was done at RHIC before. As you know, and we have sort of triggers that arrive at a frequency of about 15 kilohertz. And for each of these triggers, we need to read out the TPC for a number of microseconds as the charge drifts from where it is produced in the TPC to the readout plane. And if you think then of PP collisions, a 15 kilohertz trigger rate, which is introduced in the experiment through the calorimeter electronics. 15 kilohertz trigger rate means that you would, out of the 2.5 kilohertz, 2.5 megahertz collision rate at RHIC, you would take only, what is it, 6%? No, 2.5 divided by 100, 0.6%. However, our tracking system operates in the streaming readout mode, which means that in principle, the connection between the data that we take in the tracker and the data that we take in the triggered calorimeters is not one-to-one. And we can then invent a hybrid readout mode where for each trigger in the calorimeter, we read out all the tracking detectors for a window that is somewhat longer than necessary, and thereby collect a large chunk of the minimum bias collisions that we don't trigger on in the calorimeter. And for example, if you extend this window such that you this opportunistic window such that you cover 10% of the time of the real time that the detector takes data, well, instead of 15 kilohertz, you collect PP collisions at 250 kilohertz. And if you then do the math a little more carefully, you'll find that with increasing your data volume by about 50%, so there's a price to pay, you can increase the rate for untriggerable probes, like low PT heavy flavor or very low PT jets, by 2 orders of magnitude or more. And that allows you to really make measurements with a direct comparison of proton-proton collisions and heavy ion collisions at comparable statistics, for example, for RIA versus let's say less desirable options like RCP, R-Pythia, R-star RIA, etc., etc. And I think this will really be a very big step forward by collecting more of the available, far more of the available PP statistics than was possible at RHIC before. And then finally, another new device that we added last year is the event plane detector, follows the design of the star event plane detector, covers rapidity 2 to not quite 5, was funded by the NSF. is now being put together at Lehigh under the direction of Rosie Reed with help from Colorado, and will give us a vast improvement in our event plane resolution, which then directly translates into the statistical uncertainty for any azimuthally dependent measurements of jets or heavy flavor that we plan to make. And so this really, with a very, very moderate investment, again, allows us to make a big step forward, maybe not so much in terms of resolution compared to STAR, although yes, compared to sPHENIX, but in the combination of high resolution event plane determination and very high statistics for the probes that we want to measure relative to the event plane. So that will also make a big difference. Now, here, this is a schedule of the installation going on right now, supposed to end somewhere around Christmas. This is what you saw before. The outer HCAL has been assembled. Actually, we are now here in the stage where we are putting the platform for the electronics racks on top. The run next week is over. We'll open the shield wall, then the detector will be rolled in the interaction region. In the fall, will be connected to the cryo system. Then we will do magnet mapping, and then the TPC can go in, and the beam pipe, the inner detectors, and then we'll wrap everything up and have about a couple of months for commissioning and testing, which is very, very tight, but that's the schedule that the scheduling gods have given us, and we will do our best to be ready for beam in 10 months from today. So, okay, this slide is a month old, so this should be reading 10 months by now. We're here, we'll start data taking in 23, and then the agreed upon schedule is a 3-year data taking period with gold, PP, P-gold, and gold runs. Of course, here at the end of that time, construction of the EIC has to begin, and only should that be delayed for whatever reason, can we think about additional running for sPHENIX. The 3-year run plan here shown very briefly: gold, PP, P-gold, gold, with the real production runs being the runs in 24, 25, 23 will be highest priority spent, making sure that the detector actually works, that we understand the detector and can take good data with it. That will take most of that run. Hopefully at the end we will be able to use some of it to for physics, maybe the last couple of months of that run. As I said, if there's an opportunity to run longer, beyond 25, of course, there are many interesting things to do. Most of the sPHENIX measurements will not be systematics limited after run 25, but we will have to see. This is determined by the EIC schedule. I'm not going to speculate about that. So let me, the remaining minutes, if there are any, let me talk about some example measurements related to these 3 pillars of the hot QCD studies. As I said before, I think if by some miracle we have time, I can find slides related to cold QCD, but I think I will run out the clock with some of these examples. Starting with the upsilon spectroscopy, well, there's not that much to say there. At the moment, we have focused studies of Quarkonia really on the upsilon. We have the mass resolution to clearly separate the 3 members of the upsilon family. And then we expect, based on what we know from the LHC and the first measurements of STAR, that these, in particular, the higher mass states will be suppressed, probably to the extent that it will be very challenging to see the 3S. I think it was very good to see that CMS now has actually made the measurement of the 3S. I think that will be a challenge for us, but we should definitely be able to clearly resolve the 2S peak. And that I think these measurements will be extended to other quark-gluon states as a minimum high PT J size. Let's look at some heavy flavor plots. Because here the idea is that the measurements, new measurements that we do at RHIC will really complement the measurements at the LHC to allow a more detailed investigation of the temperature dependence of the diffusion coefficient than is possible with the LHC data combined with the present RHIC data alone. Okay. For both our hardware and other parts of our software, we're not too proud to borrow from other experiments. A lot of our heavy flavor reconstruction is based on KF particle that we imported from CBM, and try to then have a comprehensive reconstruction of all sorts of decays that our graduate students can analyze. I'm not going to try to explain what is going on in this diagram. Let me just show some of the particles that we believe we will be able to reconstruct with high precision. D zeros, D plus, D star plus, D plus S, and so on. And I should say that these are Pythia studies that really are used to test the reconstruction package. They are not reflective of the actual statistics that we will that we are expecting to collect, but they give an impression of what these particles look like in our reconstruction. If we use the performance that we study with these plots and then do a fast simulation to project the expected statistics, you see what we expect here on the left in combination of proton-proton from the streaming readout and gold-gold in terms of RIA for displaced D mesons coming from B decays and prompt D zeros. And you see that we expect to have really an excellent statistics over a large range in PT for the Ds, and I would say good to very good statistics for the displaced Ds. Similarly, we can use these particles and the event plane information from the SEPD to do precise measurements as a function of PT of V2, both for Ds and for B mesons, for B hadrons through the decay into Ds. And again, I mean, for the right-hand plot, I think it is important to stress that the streaming readout, high statistics PP sample is really a qualitative step forward at RHIC. You can, of course, also measure lambda Cs. And again, for the first time, we'll be able to do that at RHIC with high precision, also in proton-proton collisions. And I think those are some examples that give you a sort of a flavor of what to expect from our heavy flavor program, pun not intended. On the jet side, let me just point out, I mean, the biggest step forward comes, of course, from just a basic increase in the available statistics compared to present measurements, which for charged hadrons or jets is sufficient to extend the kinematic reach by about a factor of 2 or 3. Of course, what do you get from extending kinematic range? Well, as I'll show later, you get overlap with the LHC over a wide range in PT, where you can do the same measurement at RHIC and at the LHC. We are still not quite going to reach the gold statistics in PP collisions, but we're going to get much closer than was possible previously at RHIC. I mean, the RHIC PP luminosity just isn't high enough to match what one can do at the LHC. Then we have an empty slide. And here's some day one physics measurements that we can do. So standard stuff, dijet asymmetries, photon jet balance, and fragmentation functions. Why are these day one measurements? Well, these have relatively high jet PT, and high at RHIC definitely, and therefore you can learn about the underlying jet physics from these measurements without complicated deconvolution unfolding procedures, illustrated here by the fact that if you reconstruct just PP events or the PP event embedded in gold-gold, you get essentially the same distribution. So this will allow a direct comparison of PP and gold-gold without unfolding. And that is something that I think will be among the first measurements that you can expect from sPHENIX. Of course, as I mentioned before, we have the SEPD. You can measure jet V2, which is interesting in gold-gold. But I think if you look at the Atlas measurements in P-lead, potentially even more interesting in P-gold, where data from sPHENIX hopefully will help us understand where the observed high PT asymmetry in anisotropy in PA collisions actually comes from. And again, this is enabled by the calorimetric jet trigger, by the stream readout for the hadrons, and by the SEPD that we are installing. So that I think will hopefully add to a piece to the puzzle of whether there are signs of jet quenching in PA collisions or not. As I said, I mean, one of the key considerations was the overlap in kinematic reach that you can achieve between the LHC and sPHENIX, where there's sort of a golden region between, say, 25 and 50 GeV, where the highest PT jets or the highest PT photon jet events here that we see that we will see in sPHENIX overlap with the lowest PT jets for which, let's say, CMS and Atlas still have control over their jet energy scale, let's say down to 25 GeV. So I think that direct comparison will be quite illuminating. And there's a topic that I think is closer to the heart of several of those connected, which is seeing how the back-to-back nature of dijets or photon jet events or jet hadron correlations is modified in heavy ion events compared to proton-proton collisions. Here, there's a distinct advantage of the lower collision energy at RHIC, because the kinematics just dictates that there's not as much phase space for initial or final state radiation. So the correlation in back-to-back angle between, let's say, dijets or photon jets is much tighter, and therefore teasing out changes in that correlation between PP and AA is going to be much easier at RHIC. I think for those of you who paid attention at Quark-Matter last week, this really the importance of having additional measurements in this addressing this particular question, I think it was highlighted by the ALICE and STAR results. Here's the ALICE measurement of the angular correlation between jets and hadronic recoil, which shows a surprisingly large effect for R equals 0.4 jets in the lowest PT selection. And this adds, together with similar STAR results and other analyses, to a very complex picture of these angular correlations, where for high PT photons, there's no effect seen in Atlas and CMS measurements. The CMS C-jet measurement shows a narrowing of this correlation. And here we see in some selection the significant broadening of the correlation. So clearly there's a lot of opportunity both for further experimental study and for insights on the theory. And I think I should start wrapping up. Let me just point out one additional really new capability where we can combine the jets that we measure with the calorimeter with tagging observables from the tracker, I mean, either the multiplicity or secondary vertices, to tag B jets using methods that are very well developed at the LHC. And that will allow us to get good precision measurements of B jet RIA or B jet V2. And again, if you paid attention at Quark Matter, then you see that there's definitely definitely open questions on the B jet side. I will also come back to that in a moment. Okay, so then once we have run sPHENIX for 3 years, what are we going to do with the data? And I think this has to be seen in the context of an effort that is ongoing, has been ongoing for a while, but I think needs to be put on a even more, let's say, comprehensive and systematic footing, trying to combine data from RHIC, from LHC, from different experiments and from different observables in a well-controlled statistical approach based on Bayesian inference to extract really physics observables that you cannot constrain with a single measurement and a single model comparison, like the temperature dependence of the various transport coefficients. As I said, there's an effort on many fronts ongoing, but I think this really needs to be further developed and put on a somewhat more systematic footing through a close collaboration of experiments and theory. The other thing, and that's something that well, I think many of us have been noticing over the years, but it has not quite been addressed yet, and keeps coming up, is the fact that there's a lot of work left on the experimental side. I think we have seen a lot of new measurements. We have also seen some old measurements being redone. And I think it is just the fact that the repeatability of some of these measurements isn't always immediately evident when you compare new measurements and old measurements. Here's a recent example where Alice studies the ratio of RIA for large jets compared to small jets and finds that the large jets are more suppressed, which, however, is not exactly what Atlas saw in this RCP measurement almost 10 years ago, where the larger jets were less suppressed. And of course, then both of those can somehow be extrapolated to the CMS measurement, which shows no R dependence of the jet suppression. So clearly, this is an example where, as a field, we have to put on our thinking caps and figure out how to reconcile various measurements that are not exactly the same, but seem to be at least cousins of each other and should show some relationship. This is maybe even more obvious when you look at B jets. I mentioned that already. There's a 10-year-old, not quite, yeah, almost 10-year-old CMS measurement of B jet RIA that was now also done by Atlas. Higher collision energy, slightly different methodology, but and somewhat different physics conclusions, whereas CMS saw no difference in RIA of B-tech jets versus light hadron jets. Atlas sees less of a suppression of the B jets. It's it's not different by factors compared to the systematic uncertainties, but it really suggests that one of the things that we need to do on the experimental side is to really, at some point, go in a systematic manner about reconciling apparent discrepancies or tensions between various measurements. And these are just two examples from quark matter. It's by far not the only examples. I would say measurements done sort of at the limits of our capabilities have a tendency in the majority to have agreement only sort of at the edge of the systematic uncertainty. So on the experimental side, there's a lot of work left to be done by the existing experiments and by sPHENIX, which I think will provide, in addition to new measurements, extremely important redundancy with additional measurements of things that we have seen at the LHC or seen at RHIC. So a lot of work to be done, both for the theorists and the experimentalists. And that brings me to my summary. Very simple. sPHENIX has been designed to add new capabilities to the RHIC physics program, providing some of the detector capabilities that have been exploited very successfully at the LHC, particularly for jets and open and hidden heavy flavor. The detector is on track for start of data taking in early 2023. It will require a lot of work by our 400 collaborators and the support at RHIC, but we are looking forward to getting that done. And I think it will provide a really exciting opportunity for a direct comparison of RHIC and LHC hard probe measurements, and in combination then also input to really move our theoretical understanding forward. And that's what I wanted to say.
Thank you, Professor Gunther, for this very exciting and comprehensive talk. Any questions? Shinyan, please go ahead.
Yeah, hi, Gunther. Thanks for the talk. I have two questions. One is related to the this azimuth angle broadening you just raised up, and then you said comparing to, at least the data is at very low PD, is between 10 and 20 GeV, and I think when you said Atlas is Z-type jet, when you say intermediate jet, what is the PD range of the intermediate?
So that was the CMS measurement that I was referring to. I have to check,
okay.
But it's sort of 50 GeV-ish.
Yeah, so that's a significantly larger PT than the Alice. Yeah. And you can see the Alice that when at large PD, even between 20 and 30, they already don't see the broadening anymore.
Yeah. So that is if I just go there, I'm
strictly sort of PD.
Looking at in this with the normalization here, it's not immediately easy to tell by eye what the shape is for the highest PT, but clearly there's no.
Yeah, you see that at their high PT level, they also have narrowing. This is.
I'm not sure if you can see that from this plot, but it is definitely not broadening. I think that we.
It's not very high PT, definitely not.
And well, this is a very exciting measurement. I think this is something that we look forward to doing as well in various forms. Clearly we can we will probably steal the recoil. The hadron jet recoil method from from Alice and Star,
at very low PD, between
any other
10 and 20 GeV jet is it's sort of tricky. So it's very tricky.
And what you need there is you have to do that on a statistical basis. Once you get to below 20 GeV or so, I think up to 20 GeV, and we should be able to do that. Sort of the traditional approach. Below, you have to really start thinking about a statistic, an ensemble-based measurement very carefully.
Yeah. I don't know whether you know this or not, but we actually had a paper predicting the narrowing of Z-type jet because of suppression of Z+2 jet. Because of that.
Okay.
Yeah. We had a paper, some time ago. Anyway, so
I'm
this
sure
is
I can
narrowing.
find that.
Yeah. I can send you the reference afterwards.
Sure.
I can send. My second question is regarding the sPHENIX. You didn't talk about any tracking capabilities, did you? Oh.
No, I'm sure I did, but it was a.
So my question is that can you actually do tracking? Like in particular, what I'm interested in is looking at the jet hadron correlation. In jet means high PT and low PT hadron is coming from the medium response. So that kind of correlation should also be interesting.
Depends on your definition of low. At the moment, I would say, at the moment, this is the tracking efficiency right now. It's close.
Yeah, your low PD
up to
is pretty.
GV, it starts dropping sort of when you get towards 500 MeV PT, it starts dropping.
That's okay. I think around 1 GeV is okay.
But
between 1 and 2 GeV is okay.
This can certainly be improved. There's no.
I see. So 1 GeV, between 1 and 2 GeV, you're still okay, right?
Yeah. That I think should be perfectly fine. This can be. The reason for this is that we have in the Monte Carlo generation, we have the full field map, including non-uniformities. The tracking code that we use, which comes from Atlas at the moment, assumes a uniform magnetic field, and that starts biting you below GeV. So this is a technical improvement on the software side that we need to negotiate with the Atlas folks.
I see.
But timer. At some point at low PT, there will be a cutoff because our magnetic field is a factor of 3 higher than in star. But above the cutoff, there's no obvious reason why the tracking capabilities would be any worse than what star has.
I see. Okay.
Yeah, jet hadron correlations in all forms should be something that is on our menu. Okay.
That's good. That's good. Yeah. Thank you.
Okay. I see Grashna has a question.
Yeah, Gunther, thank you for the very nice talk. I have 2 questions actually. Sometimes what you were showing us is just, when you go after B meson meso, that's starting from 2 GeV before, because there's no PID. This was kind of status 2 years ago. But then I remember talking with Tom, and he said that you guys will be maybe playing with some gas in TPC, that some PID will be possible. Was there any progress on this front, or you gave up totally?
No,
Tom was pretty optimistic.
We haven't given up. What I've done is so Tom had based on his measurements an estimate for the width of the Landau fluctuations for the charge in each cluster produced along the trajectory of the tracks in the TPC. And if you take that estimate and you put it into sort of a standard truncated mean estimator, so nothing fancy, you find that while the PID capabilities will not be quite as good as in ALICE or even STAR, because the track length is much shorter. Our TPC only has 75 centimeters outer radius. So the specific resolution is actually not significantly worse if Tom's expectations are are true, and then meaning that the resulting DDX resolution should be within a factor of 2 or so of what RHIC gets with a 4 times larger TPC, square root of 4. And so there's a lot that you can do with that, and I think that will eventually help extending towards lower PT. But beyond studies that I could do sort of on the back of the envelope, we really haven't systematically tried to exploit that, because from the very beginning we said that we have to do the most important physics without relying on the DDX, and if in the end we can use DDX as then that's a bonus. Yeah. But we will certainly try that once we have put everything together.
Right. And if I may, another question. This past 2 years were very difficult, and I know very well how MVTX is affected, but I would like to ask you, is there any other system which is suffering from perhaps some delays and not being ready for February 23? Is there anything which is doubtful at this point, or you think everything will come together eventually? This is very short time scale. It's very ambitious.
It is. So first of all, I think it is quite miraculous that we, after have been able to stick to the schedule as much as we have. And the goal is still to be ready in February 23. We had long discussions about the schedule in the last months, and redid the schedule a couple of times. And in the end, this is our best estimate of the earliest time at which we can be ready, February 23. And that's
with all systems, right?
Work to, and that's with all detector systems. As you have seen, I mean, most of the hardware is in place. I think the system where there are some electronics parts for the electronics, some chips that we are waiting for, and well, if the delivery timelines were as they used to be, it would be no problem at all. At the moment, there's a certain amount of uncertainty. So there's some fraction of calorimeter electronics spares or so that well, we have to see when the components arrive, and I think that to some extent may also affect some the CDC electronics we have to see, and the readout for the readout electronics for the SEPD. I think they're, well, we have to see when the chips arrive. But all the major hardware components at the moment we are expecting to be ready. I mean, the MVTX I think is probably a few hundred yards from where you are at most. I don't remember the layout of Berkeley that well. So
yes.
that is ready. The calorimeters are ready. The electromagnetic calorimeter is ready. The TPC, the readout chambers are ready. The field cage is ready. Really, the electronics for most of the detectors are in hand, but that's, I would say, one of the greatest risks. A few weeks ago, we had a couple of days delay because we couldn't get just plain bolts. I mean, you can't go to the Home Depot to get those, but normally you just order them and you have them the next day to screw the support for the RHIC platform on top of the magnet, on top of the autohadronic calorimeter. And well, there were no bolts available anywhere, so it's a challenging environment in which to operate. But up until the last moment, we are going to we're going to operate under the assumption that February 23 is the start date. That's the goal.
Okay, thank you.
Yeah.
Okay. Okay. I just have a question, maybe just a clarification on the BJT array plot that you showed at the very end between Atlas and CMS. There's very small uncertainty from the end part, I suppose, right? That is shown at 1 from Atlas. Do you know why it's very small?
I would say this has been a mystery to me for a while. I think Atlas is more ambitious than the corresponding systematic uncertainties than CMS is. I don't know. I mean, there are some. I mean, we all estimate our systematic uncertainties independently, and I don't think we in CMS have fully understood what Atlas is doing to get such a much smaller estimate than we do. I mean, I think if you look at the jet measurements itself, there are also some areas where Atlas is more confident in their systematic uncertainties than CMS. Yeah. So I don't have the answer here. I think you would really have to dig quite into the details of how that estimate is done. I don't think I have any obvious reason for where that comes from.
But this has some global modeling uncertainty into it, right? And usually that is not so small.
I mean, I think one important uncertainty there is your estimate of which fraction of the total inelastic cross section your trigger is actually sensitive to. And I don't, I haven't followed CMS or Atlas that closely in the last 6 years, been busy with sPHENIX. There you can do, the collision rate at LHC is high enough that you can do quite a bit there with so zero bias collisions where you just record data at every beam crossing. But I don't know the details of how Atlas or CMS have come up with the latest estimates of which fraction of the cross section they are sensitive to. Okay, I don't want to start speculating.
Okay, yeah, I see. Yeah,
specific.
Yeah, I see. Yeah. Okay. Yeah.
This is the,
okay. Yeah.
Okay, I will speculate, even though I said I wouldn't. This is a moving goal at LHC because of the high radiation load. The minimum bias detectors that the experiments use are actually subject to significant aging, and you really need to be very careful in estimating the minimum bias efficiencies that you use in figuring out which fraction of the total cross section you see. Yeah.
Okay. Yeah. Okay. Thanks. Yes. And just one more question for the lambda C plot that you showed. Is that without the PID? That the very small uncertainties.
All the plots are with. Oops, where is it? Here. All the plots are done without PID. Without PID, we think we will be able to do better with the DDX, the PID TPC, but the baseline is no PID. At some point, some of your colleagues at at Berkeley evaluated how much additional PID would help, and it is significant, but in the end, that was just not feasible from a sort of scheduling point of view to add a significant new detector in the gap between the D and the EM help.
Okay. Yeah, I think if you want to go to lower PT, then you need a better PID. Yeah. Okay. Any other questions from anyone? Okay. Seems not. Then I think that's all we have for today. Thanks once again, Gunther, for this very nice talk and taking the time to talk to us.
It was my pleasure. I hope I'll have a chance to talk to you in person in the not too distant.
Well, first of all, we in the future, if any person would like to come to give talk in person, we should be able to do that.
Yeah. I've now just started traveling to Brookhaven again. Up until February 20, I was going there every other week at least, but then for 2 years I didn't go at all, and now made one trip in March, and I think soon I'll start going there again every other week. Yeah.
We will have a couple of speakers in the summer, and who might be interested in coming over, to visit.
Yeah.
Well, thank you.
Okay. Thank you.
Bye-bye.
Okay. Thank you. Bye.
Thank you. Bye-bye.
Oh, Gunther, don't forget to send your slides to Suraj.
Yeah, I'll do that.
Yeah, thank you.
Okay. Bye-bye.
All right.